Hello, I'm Susan Krumdijk, Professor of Mechanical Engineering, and you have found the Transition Engineering Podcast, where we talk about how to make the energy transition work. Welcome to the Transition Engineering Podcast. I'm here with Philip.
Hello.
And I'm Susan Krumdijk, your host as usual. And this is our first regular podcast. We would like to start at the beginning. We are working on transition engineering, and people usually ask me what I mean by that. What does transition engineering mean? And it's pretty simple. Can you think of any transitions we need to make?
Yes, of course. I do.
Well, if you need to do something, you probably need to call an engineer.
Yes.
So we are looking at the emergence of a field whose job is to figure out how to transition to sustainable energy, basically, and sustainable everything else. And what do we mean by sustainable? Well, we've been working on that for years, haven't we? What we mean right now is reducing the amount of fossil fuel that is dug out of the ground, used, and put in the air. So we're going to keep it simple. And we're going to see how it goes, because today we're going to talk about, yes, climate change, global warming, carbon emissions. You got to start at the beginning, don't you? All right. Now, what we thought we'd do to keep it different, because I'm 50-something, and young Philip here is, how old are you?
I'm 21.
21. Oh my God, baby.
21.
So Philip's 21. And Philip, you've heard about climate change, haven't you?
I did. I can't remember when it was the first time, but I believe it's been around a while.
Yeah. And when you hear about it, do people use the words global warming, climate change?
Yeah, they do. But I believe at first I heard global warming.
Right. All right. So they actually are kind of the same problem. Greenhouse gas is causing global warming, and that causes climate change. So it is sort of a sequential thing. I want to first start out by taking global warming and just translating it into engineering language, because I think that would be fun. You've probably heard of greenhouse gas emissions and the greenhouse effect. And yes, all of us engineers with a thermal background should be able to grasp that. But let's just say it like this. There is a thing we know, and that is that energy is conserved. Energy balances. So you have to define a system on which the energy balances. And once you define a system, we know that the rate of energy into the system minus the rate at which energy leaves the system has to be equal to the amount of energy stored in the system plus the energy generated in the system. Right, that's the rule. You remember that from thermo class?
Yes.
All right.
Long time ago.
But it's pretty simple. That's why you can remember it.
Yes.
And if you do an energy balance on the mass of a system, a control mass energy balance, then you say the rate of energy stored in the system has to be equal to the mass times the specific heat of the system times the rate of temperature change in the system.
Over time, yeah.
Yes. So the first one is the global warming, because the rate of energy absorbed in the system is greater than zero.
Yes, it's an imbalance.
And according to scientists, that rate at which energy is being stored in the planetary system is about 4 watts per square meter. And that, therefore, is causing a temperature increase in the system with time.
Yep.
And of course, that temperature increase is causing all sorts of changes in the climate, in how fluid flow is moving around, how much water can be transported. You will remember the humidity relations?
Yes, yeah.
Sort of, yeah.
Yeah, sort of, yeah.
Okay.
But,
warmer air can carry more moisture. Yes. So we're talking about a lot of climate and weather changes because of this temperature increase. So that should be pretty simple. Now, the thing I'm interested to talk about with a young fella is that I like how climate change feels like a new thing, right? It's a new emergency. It's an emerging crisis.
It feels like it, yeah.
Yeah.
Really.
But what's funny is it's not. We're going to go through a little bit of history of the issue of climate change and global warming, and then we're going to see if we can get in our heads as engineers a really simple understanding of what the requirements of the problem are. Does that sound fair?
All right, let's do this.
Okay. So if we go back in time, we know that in 1896, a famous chemist named Savant Arrhenius, a Swedish scientist, looked at how fast people were burning coal and said, you know what? We could actually be changing the climate. We could change how much heat is kept in the thermal system of the planet.
Really?
And yes, 1896. And he actually put it out as a warning.
Really?
Yes, that burning all this coal could change the planet. And that in 350 years or so, we could actually double the amount of CO2 in the atmosphere. And that would have a profound effect on everything.
1896.
Yes.
It's a long time ago.
That is a long time ago. And then, well, his model probably wasn't inaccurate, that if we doubled the amount of CO2 in the atmosphere, it would have a profound effect on everything. But 350 years from now, who is actually going to worry about that? Nobody. So it sort of wasn't a big problem for a while, but it was known. We're going to jump forward in time to 1924, when another physicist calculated that burning coal at the current rates in 1924, because of course the rates of burning coal had gone up quite a bit, this could double the atmospheric CO2 within 500 years. Well, by then they were starting to see that some of the CO2 was being absorbed in the oceans and in the land. And so that gave even more time for this to become a problem. So while it's a known phenomena, the urgency of the problem is what's been missing, because it wasn't urgent then. We get to cut these guys some slack. It wasn't actually urgent.
Yeah,
it was known, but not urgent. Not a problem.
It's not really urgent, yeah.
All right. Then in 1948, people were really starting to look into what was going on with the oceans. The fact that they, if there's more CO2 in the atmosphere above water, then the water absorbs more. It's just diffusion, simple diffusion and dissolution, and it's just the way it goes. So actually, 1948, a report says that we really don't have to be worried about CO2 emissions because the ocean will suck up an awful lot of it. So the oceans will regulate the carbon emissions. So that sounded pretty good. Then in 1958, a scientist named Keeling set up a measurement of CO2 at the Mauna Loa Institute in Hawaii. Mauna Loa observation in Hawaii. And that measurement was quite accurate. And it was continuous every year measuring. You can Google it, the Mauna Loa Observatory.
Okay.
And it didn't take long of these measurements to see that actually, in fact, the CO2 was definitely accumulating in the atmosphere.
Yeah.
So it's really that Mauna Loa CO2 concentration curves, which started to get people thinking, okay, maybe there is a problem. And also the measurement of CO2 going up in the atmosphere, and coupled with the amount of CO2 produced every year, right? We're on this exponential curve of increasing fossil fuel consumption every year.
They didn't think about it before, right?
Well, we were at the bottom of the exponential growth curve. Once you start up it, things get more interesting very quickly.
And they were calculating that the CO2 rates will level within 500 years. They didn't think about that the CO2 could accumulate.
True, because it was going to go in the oceans.
Right.
Right. So, by the 1970s, you started to have the climate science coming in, where people were modeling what would happen to the Earth's climate with different amounts of CO2. And that's where, I think alarm bells started going off that the rate of accumulation is really speeding up. The rate at which we're emitting carbon is speeding up. Yeah, a lot of it's going into the ocean, but a lot of it is staying in the atmosphere, and this could be a problem.
Yes.
So in 1985, the United Nations set up a conference saying, look, this accumulating CO2 it's going to change the planet. It's going to warm the globe. And in 1990, 49 Nobel Prize winners got together and put together a statement to the world saying the buildup of various gases introduced by human activity has the potential to produce climate change, dramatic changes in the climate. So, like I said, it's not the actual physics, the actual thermodynamics has been known for a long time. What are we up to now? Let's say 1990. We have this international body called the International Panel on Climate Change was organized, and it had 170 scientists in it. You know, it's got 10 times that now, right?
Yeah.
There's a lot of science. Oh, no,
Yeah.
100 times that. What am I saying?
Yeah.
And so in 1990, that panel recommended that a 60% reduction in CO2 emissions was needed to stop CO2 emissions. And it was about that time that the fossil carbon emissions each year were about 4.4 gigatons of carbon per year. So this is the actual carbon, not carbon dioxide. And the atmospheric CO2 emissions had already climbed over 350 parts per million.
That's a lot.
Right. And so the climate science by the mid-1990s had already shown that 350 parts per million was definitely enough to cause dramatic climate change.
Yeah.
And we were already there.
1990, yeah.
1990. So the mission from that point, there were a lot of people who got, you started to see climate action groups saying, okay, look, we got to reduce our carbon emissions by 60%. That's what the scientists say. In 1997, the Kyoto Protocol was agreed on, and that agreement was ratified by a lot of the nations on the planet. And what were they agreeing to? They said, we're going to limit our emissions. By 2012, we're going to bring our emissions back down to the level in 1990. And 1998 was the hottest year on record. And that started the march of hottest years on record, which has been going on since then.
Yes, it did.
So the data continues to accumulate, and we got a long way to go till 2012. It seemed like a long time away.
Yeah.
In 1997, 2012 seemed like a long time in the future.
Yeah.
We can get our carbon emissions down. We'll have technology to limit emissions.
That backfired.
Or something. Right. I think now, looking around, I think only Japan has met that requirement.
I don't know that exactly, but could be.
Right. They have had a prolonged economic recession. So maybe that's why, don't know.
Right.
But yeah, the countries of the world have not done a great job at meeting that Kyoto Protocol. So in the 2000s, we have accelerating alarm, because by 2001, the CO2 accumulation in the atmosphere was up over 370 parts per million. In 2001, the U.S. Global Climate Research Program said, look, there's a much higher probability of extreme weather, drought, flood, storm, sea level rise, because of where we're at, 370 parts per million.
Yeah.
We get the ratification of the Kyoto Protocol. We get numerous scientists saying, hey, the Arctic sea ice is thinning. The extent of the sea ice is shrinking. The huge icebergs calving off of Antarctica, things we haven't seen before. And the Greenland ice sheet is melting at rates we've never seen before. And by 2012, we've got CO2 accumulation in the atmosphere pushing up over 390 parts per million. In 2012, NASA Chief Climate Scientist Dr. James Hansen said, look, the target that has been talked about in international negotiation for a 2-degree warming is actually a prescription for long-term disaster. And we're going to talk about that 2-degree limit for a while, because here just recently in 2015, the IPCC fifth assessment report came out and said, look, 85% of the known fossil fuel reserves must remain unburned, unproduced, in the ground in order to limit the global warming to 2 degrees C.
85%.
85% of what we now know exists.
Oh, that's a lot.
Has to stay in the ground. So that's recently. And then in 2015, the Coalition of Partner Nations, COP21, got together in Paris. 195 nations signed an agreement to limit global warming well below 2 degrees C by rapidly reducing emissions. And yes, the CO2 emissions in the atmosphere had accumulated and pushed over 400 parts per million. All right, I'm old enough that I actually remember back in the 90s that 400 parts per million sounded like it was a really long time away. It sounded like something that we certainly were not going to do. No, we're not going to do that.
Yeah.
And yes, we're doing it. And 2006 was the 3rd consecutive year of record global temperatures. It looks like now the global average is over 0.8 degrees C, and we are well on our way to 1.1 degree warming within the next couple of years. And fossil fuel emissions are now over 10 gigatons per year. So yeah, in the early 1900s, with emissions at about 0.3 gigatons a year, it's easy to see why it was known but not alarming.
Yeah.
And why now, at emissions over 10 gigatons a year with parts per million over 400, why it is an alarming problem and one that requires action. Now you've heard that a lot, climate action, right?
Yes, of course.
Right, that is part of the vocabulary now.
Yeah.
All right, so we're going to turn this around and make it an engineering problem.
Okay.
Fair enough?
Fair enough.
Because, okay, do you feel a little like wrung out or helpless? I mean, understand the problem, but...
Yes, observing it.
But what's the what are we going to do?
Yeah, right.
People have known for a long time. What has been done?
Not that much.
Not that much.
Not that much.
And yet, we want to hear about what is being done and how we're not going to do this and how we're going to save the planet. We definitely want to hear about that. And yet, objectively, not much. So if we think that in taking on a new type of engineering where we are going to do this thing, right? We're going to figure out what to do. That we need the requirements of the problem. We need the problem definition and we need the requirements of the problem.
Yes.
Right? That's what'll work. Well, at least we'll get started. So, the requirements of the problem. And this is what you might not have really caught on to. The problem is that fossil carbon is being removed from the ground where it's been for 150 million years and put into the world now. 150 million years ago, have you watched Jurassic Park?
Yeah.
Yeah, the world was a little different then.
Yeah.
And it was different in a lot of climate ways as well as species ways. The climate was different in that there were no ice caps. Mm-hmm. There wasn't a cold place.
Yeah, it was warmer.
There weren't high mountain ridges. It was warmer. Things were growing like crazy. And in fact, plants and animals were growing so fast that the decomposition couldn't keep up with it. And that's why the carbon accumulated.
Yeah.
All right. So that ecosystem is different from ours, that's for sure. So now we're taking that fossil carbon and putting it back into the system and seeing what happens. When carbon first started becoming a fuel, so coal, we would say that around 1800 is when that really started taking off. And we're going to be talking in terms of gigatons of solid carbon. And I'm keeping it solid so that we can keep it real. Because it's the work of digging those tons of coal and oil and gas out of the ground and putting them in the air that our people, engineers, have been getting so good at.
Yeah.
So we're not going to talk about emissions. We're going to talk about carbon.
Okay.
The actual stuff that needs to stay in the ground.
Yeah.
All right. So from 1800 to 1960, I was born in the 60s. That's a long time. That's 160 years. Over 160 years, it took that long for 100 gigatons of carbon to be taken out of the ground and put in the air.
Okay, 160 years for 100 gigatons.
Right.
All right, good.
So in 1800, we started out at 290 parts per million.
Mm-hmm.
All right, now here's the bad news. Those 100 gigatons of carbon that got put into the air can't be taken back out.
Yeah.
They're there, and they're going to stay there. That's what we mean by accumulation. So now we're going to start building a mind picture, all right?
Okay.
The climate scientists tell us that there's a system called the climate, and it gets unstabilized if we put too much carbon in the air. I want you to picture a bridge. That's a system that's very useful. We use it to get across things, right? Get across a river.
Okay.
All right. In engineering terms, there's a lot of ways we can build a bridge. It could be for pedestrians, it could be for trains, it could be for traffic. And what we know when that bridge is built is we know what the foundations are, we know what the maximum anticipated flood might be, we know what the traffic might be, and we know what the structure is we're going to use and what the materials are. So therefore, what do we know about that bridge?
How many it can take.
Right, what the load limit is.
Right.
The maximum load. And if you've ever driven across a bridge, which you have,
Yes.
you will see that they have a sign on it
Yeah.
that says maximum load.
Yeah.
And especially if it's a small bridge, because they don't want people taking a giant truck on the bridge.
Right, yeah.
Or a bunch of trucks.
Yeah,
All right.
right.
So the bridge is a useful system. Don't overload it.
Mm-hmm.
What happens if you do overload it?
It collapses.
It could. Actually, we don't know, do we? We know collapse is one of the things that could happen. That's the worst thing that could happen.
Right.
But
It's
could we tell you exactly how much overload it would take to collapse it?
maybe. We can.
Well, we know what not to go over. That, and we would call that the safety limit.
We have
right?
a safety limit, yeah.
Don't go over this limit because the risk of something bad happening increases.
Okay.
So if we go over the safe load limit, there could be a crack.
Yeah.
A crack that develops in one of the columns. There could be an undermining of a foundation. There could be all number of things that could happen, but they all make that bridge less safe. And especially if, say, there's a little bit of seismic activity or if there's a high flood, you know, any little perturbation is now amplified because of this damage to the bridge. So that's the analogy we're going to use for the planet's climate system is this bridge. We could probably not tell you exactly what the damage would be on what column to what part of the structure if you overload it, but we can tell you not to do it.
Right. You can.
And we can tell you that the risk of catastrophic failure increases with every amount you go over the safety limit and past the load limit.
Yep.
So we've loaded up our bridge with 100 tons of carbon. What do you think?
That's a lot.
That's a lot. The climate science says, do not overload this bridge. Do not go above 800 tons.
800, okay.
800 gigatons of carbon.
All right.
We've put 100 on.
Yeah.
Well.
1/8.
So. Yeah. No wonder no one was worried in the 1960s.
Yes.
All right. So we're going along. The economy's growing, digging up a lot more coal, and now we're adding oil to it and gas. How long do you suppose it takes to add the next? Imagine that we're loading up this bridge with trucks full of carbon. Mm-hmm. So our first truck held 100 tons, and we got that on, but now it's stuck there. It can't get off.
Okay.
How long does it take to add the next 100 gigatons?
The first 100 were produced in 160 years.
Right.
So maybe half of the time, because the economy is rising and population is rising, and
so everything. Assuming we double the rate or something.
Yeah.
Well, that's a good guess, but I'll tell you what, we had exponential growth.
Oh, okay.
Yes, we did. We had exponential growth during that time. So it only took 20 years to get the next 100 gigaton truck on that bridge. Ooh. It did 20 years. Oh my gosh.
Yep.
Yes. So now we're up to 200. Gigatons of carbon is now in the air that wasn't there before. We've got 200 gigatons of carbon on our bridge that wasn't there before. We're still a long ways from the maximum load, right?
200.
So,
okay.
Yeah. So we've got a ways to go. We got 600 to go.
Yep.
All right. So you know what? We are on an exponential growth curve. So the next 100 gigatons only took a couple years, and the next, and the next, and it turns out that in less than 20 years, another 320 gigatons loading was added to our bridge.
In 20 years.
Yes, less than 20 years. So by 2014, 2015, we're looking at 550 gigatons have been added.
So we're coming close.
Yes, so we've got quite a load on that bridge. It's not, it's not overloaded.
No, but
quite yet.
Yeah.
But I'm sorry to say, we've gotten past the safe load limit.
Oh, we did?
Yes, because the safe load limit was 350 parts per million.
Okay.
If we hadn't gone past 350 parts per million, it's possible that the globe would have warmed, but it wouldn't have caused dramatic climate change.
Okay. 350 was the safe
because
one.
we'd only be talking about like half a degree or something like that of warming, and possibly the feedback loops in the system might have taken up some of that and might have equilibrated, but because we didn't stop putting carbon in, we kept going, we blew right past the 350 parts per million.
Okay, where are we now?
So we're at 400 parts per million now.
All right.
So we have already strained our system. There are already cracks in the bridge. We haven't gone over the maximum failure limit, but we have exceeded the safe load limit.
Yeah, we did.
Did already. Already done.
Yeah.
Present for you, young Philip.
2014.
I know.
Yeah.
What?
So,
why didn't somebody do something?
I don't know.
Ah, right. Well, is it looking at the bright side to say, well, we've still got 250 gigatons to go before we actually hit the failure limit?
No, it's not. Definitely
it's
not.
No.
No.
Surely it's a long ways in the future.
Yeah.
250 gigatons, that would take a long time to add that, wouldn't it?
Probably, but...
Well, how fast are we adding, how fast are we chewing through fossil carbon now?
A long time, but...
No, we're chewing through it. We're digging up and putting into the air 11 gigatons of carbon a year.
Okay.
So we got 250 left till we collapse the bridge. We're racing ahead at 11 per year. Worst case scenario, the ocean and the forests really can't give us any more help that they have been giving us. And we blow past 500 parts per million in the atmosphere in about 20 years.
Wow. That's pretty close.
Right.
When you look at the history.
Yeah. You'll be 41.
Yeah.
And things will be getting really rocky. Oh my gosh, that sounds like really bad news.
Yes,
and I'll still be here too. Think about it. I was born in the 60s. I'm going to plan on still being here when we hit 500 parts per million. And I'll have to look back and go, wow, that's interesting.
That escalated quickly.
Over my lifetime, we went from 310 parts per million to 500 parts per million, even though every scientist on the planet was saying, don't do that. And I was a mechanical engineer in energy, and I knew we should not do that.
Yeah.
All right, well, I got one more piece of bad news for you.
Oh, hit me.
Okay, here it is. The amount of fossil carbon, which is now economically extractable, which our economy wants and needs and desires, is up pretty close to 2,000 gigatons of carbon.
No way. 2,000.
Yeah. In other words, there's a really, really big thing which must not be done.
Ouch.
Right, and we saw that, when was it that the IPCC, 2014, 85% of all known fossil fuel reserves must remain unburned.
4 years ago. Okay.
So the requirements, if we were going to turn this really ghastly situation into engineering requirement, is there a simple way to look at this? Like, we just flip the perspective. We're going to talk about that a lot. Looking at the consequences of overloading the bridge and collapsing it, looking at the consequences of ramping the CO2 level up in the atmosphere to 500 parts per million. And remember, it isn't about leveling off how much we emit. It's not about that, because that gets us to that 500 parts per million pretty quickly, even if we just stayed at a constant rate, what we've got now, and didn't grow anymore. So the engineering requirement here appears to be that we need to look at shutting down oil platforms, capping them off. No more exploration for oil. We don't need to find any more. Found enough. No more drilling for oil. There's a lot of people working on drill rigs who are going to be doing something else.
Yeah.
The refineries that we've got, a lot of them are getting a bit old. Well, you can just plan to mothball them. And your service stations, we can start winding those down. Coal-fired power plants, a lot of them are getting old. Well, they're going to be shut down.
Okay.
And there are some countries who've said, you know what, we're going to shut down our coal plants, right? Our coal-fired power plants.
Yep.
Is Germany one of those?
Yeah, they do want to do it, but on the focus is the nuclear power plants. That's the focus right now.
Yeah, that's a big political topic, but I have actually heard that's the plan, shut down the coal. Except, on one hand, that's the plan, we're going to shut down the coal, and on the other hand, you have a 25-year extension on the biggest coal mine in Europe to keep digging the lignite out and put it in coal plants. So we definitely have this issue of what are we actually going to do compared to what do we say needs to be done. And right now, I would say that the requirement that we're going to use for transition engineering is that we're going to look at everything that uses fuel, and we're going to look at the fuel not being taken out of the ground and look at what that means for how we would change those systems. Okay. And that to me seems pretty straightforward.
Yeah,
we're going to leave the carbon in the ground. Now, we haven't yet figured out how, but at least we've got a little bit of clarity. It's not about reducing emissions, it's about reducing production.
Yeah.
And we will continue to work on what that might look like as we go through these podcasts. But at least we have clarity. Yes, we're talking about at least 80% reduction in fossil fuel use in the shortest time that you can imagine, but by 2040 for sure. Fair enough?
Fair enough,
That thing that the coalition of partners say must be done, that is our requirement. We will do it. Don't laugh, Philip.
No.
it's you know.
Yeah. It's gonna be a hard time.
Or it'll be interesting.
Yeah.
All right. Well, next time we'll talk about the decline of oil.
Okay.
And we'll look at the history of that again, the history of oil supply, the history of using oil, and the future of using oil, and we'll see what we learn from that.
All right.
All right. Talk to you next time. Thanks for joining us.
Bye.
Bye. where I try to convince you to take action. If you've already found our Transition Engineering podcast, then you might be an engineer and you might be interested in what you could possibly do to help the world change, to deal with climate change and with oil supply and resource scarcity. I'll tell you what, maybe the first place to go is to have a conversation. If you're already a member of LinkedIn, put into the groups that you're interested in the Global Association for Transition Engineering. We have a group on LinkedIn where anybody is free to put forward any ideas they have or questions, and it's just a free and open discussion forum, mostly engineers on there, where we can talk about projects that we do or ideas that we have and about the development of our field.